Hello, my amazing students. This is Mrs. A, and we are back with 6.4, which is all about the Central Limit Theorem. So remember that the Central Limit Theorem is the last section that we cover in this book. So on your test, you will have 6.1, 6.2, 6.3, 6.4. Remember, your test is coming on Tuesday. Okay, so what is the Central Limit Theorem? For all samples of the same size n with n greater than 30, the sampling distribution of the x bar, or the mean, can be approximated by a normal distribution with a mean of mu and a standard deviation of sigma divided by square root of n. Okay, so remember in 6.3 we talked about what is the sampling distribution. So now the central limit theorem is talking about the sampling distribution of the mean. And x bar is the mean of each individual sample. Okay, so we're taking all the samples, all samples of the same size n. Remember the thought with the sampling distribution was that process of taking the samples was ongoing and continuous. Okay, with n being greater than 0, the sampling distribution of x bar can be approximated by a normal distribution with the mean of mu. The mu is the population mean, and the standard deviation of the population standard deviation divided by the square root of n. N being the sample size. This is huge. Okay, so given that we have a population with any kind of distribution, it is not a population that starts normal. Any distribution has a mean of mu and a standard deviation of sigma. Simple random samples, all of size n, are selected from the population. Okay, in other words, we're taking a sampling distribution. All right, so this is the huge deal. We can start with a population that is not normal. If samples of size n is greater than or equal to 3 are drawn from any population with a mean of mu and a standard deviation of sigma, okay, then the sampling distribution of sample means approximates a normal distribution. The greater the sample size, the better the approximation. Okay, so they're saying it doesn't matter what the original population looks like. If we take a sampling distribution, then the distribution of the sample means will be normal or approximating the normal, and the more samples we have, or the more we have in each sample, the greater the approximation. Okay, if the population itself is normally distributed to start with, then the sampling distribution of the sample mean is normally distributed for any sample size n. So if we started with a normal curve in the population, then it doesn't matter what size of the samples are, we still have a normal distribution. Sampling distribution will be normal. Okay, in either case, the sampling distribution of sample means has a mean that is equal to the population mean, okay, and the sampling distribution of sample means has a variance equal to 1 over n times the variance of the population, and the standard deviation is equal to the population standard deviation divided by the square root of n. Or there's variance and there's standard deviation. So this is saying the variance of the sampling distribution of the mean is the same thing as the population variance divided by n, which is the number of items in the sample, okay? And then this is the standard deviation of the sampling distribution of the mean, and This is the standard deviation of the population divided by the square root of n, which is the number in the sample. Okay, so we call the standard deviation of the sampling distribution is called the standard error of the mean. Okay, so that is just some definitions and some formulas for you about the central limit theorem. So you can see that 6.3 and 6.4 are very tied together. So even though 6.3 did not have a lot of homework questions in it, you're using all of the knowledge from 6.3 to be able to understand what the central limit theorem is telling you. Okay, so the central limit theorem, this is pretty cool. Choose 4 birthdays. Take your own birthday month and the birthday month of 3 close members of your family or friends. Now, 4 items like that is not going to be normally distributed at all. Okay, you're going to take them, they could be very random. The birth months will be numbered 1 through 12 on the board, and we will plot our special dates on a dot plot together. Okay, now if we get a chance, we'll do this in the classroom, but I'm not going to try to do it on the little slide here. But the cool thing is even though we did not start, your own little 4 dates is not normally distributed. But when we're going to put all those dates on the board, now we're going to average, each person is going to average their 4 chosen months together and put that average on the second graph that we create. And you're going to see that although the first graph is very hodgepodge and scattered, the second graph will appear to start to look normal, even with sample sizes of only 4. Now let's figure out the mean of our original distribution and our sampling distribution. The means should be the same. What do we find? Okay, if we take the time to figure out the standard deviation of the sampling distribution should be the original standard deviation of the population divided by the square root of the number in each sample, which was 4. Okay, and we're just giving a tiny example of what the central limit theorem is all about. Okay, so let's talk about some practical rules for real applications involving a sample mean x bar. Requirements: population has a normal distribution or the sample size is greater than 30. The mean of all the values x bar is going to be equal to the mean of the population if one of those requirements is intact. Okay, the standard deviation of all the values of x bar is going to be equal to the population standard deviation divided by the square root of the sample size. And the z-score conversion of x bar. So here, remember our z-score was z is equal to x minus mu over sigma, but now we have a z-score conversion of the x bar, which is going to be x bar minus the mean over and then look at this. This is the standard deviation of the sampling distribution, which is also called the standard error of the mean. If our original population is not normally distributed, or if n is less than or equal to 30, then the distribution of x bar cannot be approximated well by a normal distribution, and in essence, the central limit theorem cannot apply. So, recap of the central limit theorem. If we have any population, this one is definitely not normal, but we have sample sizes greater than or equal to 30, then we can apply the central limit theorem. Okay, if we let me go to the next slide. If we start with a normal population, then we can have any size of samples, and we will still have the ability to apply the central limit theorem. So basically, no matter what the distribution looks like, if we have a large sample size greater than or equal to 30, we can use, it's going to approximate a normal curve. The sampling distribution of the mean is going to approximate a normal curve, and our mean of our x bars will be equal to our mean, and our standard deviation of our x bars will be equal to our population standard deviation divided by the square root of the sample size. And if we started with a normal population, the same is true. That is huge, and you're going to find out how huge it is as we go along. Okay, so here we have cellular phone bills for residents of a city have a mean of $63 and a standard deviation of 11. Okay, so now since we have cellular phone bills for residents of a city, that sounds like we have a huge number here, right? A huge population. So now let's see what we're going to do with that. Random samples of 100 cellular phone bills are drawn from this population, and the mean of each sample is determined. Okay, so we have the sample size is greater than or equal to 30. Therefore, we can apply the central limit theorem. We can know that the mean of the sample means is going to be $63, and the standard deviation of the sample means will be $11 divided by the square root of 100, which would be 10. So 11 divided by 10 would be the standard deviation of the sample means. All right. So find the mean and standard deviation of the sampling distribution and sketch a graph. So here we go. The means will be the same, and the standard deviation of the sampling distribution should always be smaller than the original. And when we divide by the square root of 100, we end up with 1.1, which is a huge factor, a factor of 10. The first one divided by 10, the population standard deviation divided by 10, much smaller. Okay, so since the sample size is greater than 30, the sampling distribution can be approximated by the normal distribution with a mean of 63, but our standard deviation is much smaller. Okay, which means all of our data is going to bunch together and be normal. Okay, notice in sampling distribution that the standard deviation or the standard error of the mean is much smaller than the population standard deviation. That's going to be a characteristic of every sampling distribution. Normal curve of sampling distribution is much narrower. Okay, so here we started with something that looked kind of like this. Remember, that was our original distribution. It's normal-ish, just because it's a large bunch of data, but not very pretty. But then, look how spread out it is. Okay, standard deviation of $11, but then when we get the sampling distribution, then it's much narrower and steeper. Okay, suppose the training heart rates of all 20-year-old athletes are normally distributed with a mean of 135 beats per minute and a standard deviation of 18 beats per minute. Okay, so random samples of size 4 are drawn from this population. Now, these are very tiny little samples, but guess what? The sampling distribution was normally distributed to start with. Okay, because it was normally distributed to start with, we can apply the central limit theorem. Okay, it says find the mean and the standard error of the mean of the sampling distribution. Then sketch a graph of the sampling distribution of sample means. So this is our original population. All right, so our means should be the same. So 135. Our standard deviation of our sampling distribution down here is equal to our population standard deviation divided by the square root of n, which is the square root of 4, which is 2, 18 divided by 9. So we're going to have a smaller standard deviation, and it's going to pull the graph in and up. All right, so always when we're doing a problem, we should check the requirements. Do the requirements for the central limit theorem apply? When working with the mean from a sample, verify that the normal distribution can be used by confirming that the original population has a normal distribution or sample size is greater than or equal to 30. Okay, so individual value or mean from a sample. Determine whether you are using a normal distribution with a single value x or the mean x bar from a sample of n values. Okay, what we're doing with the central limit theorem is we're using the mean x bar. Okay, so the individual value will have the normal z-score. So z is the individual value minus the mean over the standard deviation, like we were doing in the last chapter in 6.1 and 6.2. Okay, and then, oops, I went backwards. Sorry about that. If we are doing a mean from a sample of values, in other words, we're doing a sampling distribution, then this would be our z-score. We'd use our x bar in place of our x, and we'd use our sigma over square root of n in place of our standard deviation. Okay, so if all possible simple random samples of size n are selected from a population with mean mu and standard deviation sigma, the mean of all sample means is denoted by mean of x bar, and the standard deviation of all sample means is denoted by sigma of x bar. Mean of all values of x bar is going to be the same as the mean of the population. Standard deviation of the x bar is going to be the population standard deviation divided by the square root of n. Note, okay, this one here, which is your sigma of x bar, is called the standard error of the mean and is sometimes denoted as SEM. So applying the central limit theorem, the following histogram represents the population distribution of the weights of 600 horse jockeys. The mean of the population is 116.2 pounds, and the standard deviation is 3.9 pounds. Let us consider the sampling distribution of the sample means for samples of size n is 45. Can the central limit theorem be applied to this sampling distribution? If so, explain how the conditions are met. Since we are taking samples of size 45, and the sampling distribution, remember, means every possible sample of size 45, then yes, we can use the central limit theorem because our sample size is large enough. Okay, then it says, what is the sampling distribution's mean and what is the sampling distribution's standard deviation? Well, since we can use the central limit theorem, the mean of the population was 116.2. So doesn't that mean that the mean of the sampling distribution should also be 116.2? The standard deviation of the population was 3.9. So for the standard deviation or the standard error of the mean for the sampling distribution, we should have 3.9 divided by the square root of 45, which was our n. Okay, and then it says, what is the sampling distribution shape? And it should be normal. Even though we started with something like this, which is not normal, it is definitely skewed, our sampling distribution should be normal. Okay, so the solution. Yes, the central limit is applicable because the sample size is 45, which is greater than, n is greater than or equal to 30. Okay, so the means should be the same. The new standard deviation, the sampling the standard error of the mean should be 3.9, which was the old standard deviation of the population, divided by the square root of 45, which should be 0.58, much smaller than the original standard deviation, which brings the whole thing in. Okay, so it's going to be normal, it's going to be skinnier, and it's going to be taller. Okay, so although the original distribution was skewed to the right, the central limit theorem tells us that the sampling distribution will be approximately normal, so it will be bell-shaped. Okay, and so here is the sampling distribution of the sample means of jockey weights. N is 45. Has the same mean, but it's come in, it's been pulled in, it's now normal instead of skewed. Okay, so the following graph displays the starting salaries for law school graduates entering the workforce in 2007. Okay, does this look normal? Wow, it is really, really weird, isn't it? Okay, so this was the original population. So now it says, note, the graph is based on 23,337 salaries. A few salaries are above 200,000, and they are excluded for clarity. Reproduce with permission of blah, blah, blah. Okay, so that's just the source of this. Is a real document. This is a real curve here of data. So now it says, describe the shape of this distribution. Well, it's really, really weird. It's definitely got two big high points on it. And then it's got a bunch of weird twist and turn in between. Okay, it's hard to describe, isn't it? Consider the sampling distribution of the sample means created from this population for samples of size 25. Now, the original population was not normal, and our sample size is less than 25. Is 25, which is less than 30. Can the central limit theorem be applied in this situation? And the answer is no. Okay, so basically we are not able to do it. Let's go to the answers here. Okay, so here are the answers to this one. I think we got the slides mixed up. Okay, the distribution is best classified as bimodal, two high points. No, the central limit theorem is not applicable in this situation because neither condition is met. The sample size is not large enough, 25 is less than 30, and the population data are not normally distributed. Okay, so let's see what question C was. It says, consider the sampling distribution of the sample means created from this population for samples of size 50. Can the central limit theorem be applied to this situation? And so basically it's saying for the, it looks like I've got the same question copied twice. The answer was here, sample size 50. Okay, I got it. 25 up there, 50 down here. So for C, could we use the central limit theorem because we've got 50 in each sample? Yes, we've got a big enough sample size, so then we could use it. And then D says, consider the sampling distribution of the sample means created from this population for samples of size 200. What would you expect the shape of this distribution to be? Okay, it was bimodal to start with, but if we do a sampling distribution of sample means with a large enough sample, it should approximate a normal curve. Okay, how would it compare to the sampling distribution described in Part C? Well, in Part C, we had a sampling distribution with samples of size 50, okay? But here we have samples of size 200. Guess what's going to happen to the standard deviation? Remember, in Part C, we had the original population divided by the sample size, square root of the sample size. This would have been our standard error of the mean, and then over here on the D portion, the original standard deviation divided by the square root of 200 would be the standard error of the mean. Okay, so isn't this one going to be a much smaller standard deviation? The larger the sample size, the smaller the standard deviation, which means if this one looked like this, right, this one is going to look much narrower, okay, because it's coming in its standard deviation. All right, so here is the answer here. Yes, in C, we can use the central limit theorem because 50 was greater than the 30. We would expect the sampling distribution created from samples of size 200 to resemble a normal distribution. In fact, the larger the value of the sample size, the more normal the graph will appear. So then it follows that the sampling distribution described in Part D will more closely resemble a true normal distribution than the sampling distribution described in Part C. Okay, so they didn't talk about the standard deviation coming in, but it really does. And as you get a larger sample size, it also becomes more normal. All right, so here, this one is in your book. Okay, the elevator in the car rental building at San Francisco International Airport has a placard stating that the maximum capacity is 4,000 pounds or 27 passengers. Okay, this converts to a mean passenger weight of 148 pounds when the elevator is full. We will assume a worst case scenario in which the elevator is filled with 27 adult males. Assume that adult males have weights that are normally distributed with a mean of 189 pounds and a standard deviation of 39 pounds. Find the probability that one randomly selected adult male has a weight greater than 148 pounds. Find the probability that a sample of 27 randomly selected adult males has a mean weight greater than 148 pounds. Okay, so guess what? We are starting with a normally distributed population of males. So because we have a normally distributed population of males, our sample size is not going to be a big deal. However, in A, we're talking about selecting one, and in B, we're talking about a mean weight of 27 individuals. So that's a big difference between one and a mean of 27. Okay, so let's look and see what happens here. So on A, we're just going to use our z-score because this is a single individual. We're going to put our 148 here for our x. We're going to subtract our 189, divide by our population mean, and we're going to get negative 1.05. Okay, now that is negative 1.05 standard deviations from the mean. That would not be considered unusual, is it? Because remember, negative 2 to positive 2 standard deviations is considered normal. Now, let's look at the B part. Okay, so they're showing you, this is still the A part here. They're putting it on the chart, and they're showing that the probability that they are above that would be 0.85, because there's our mark, and we're looking above, so we're going to look on the z-score, and that will give us the area to the left, and then we do 1 minus that will give us the area to the right. So got a pretty high probability that he's going to be greater than the 148. Okay, so now for B, we can use the normal distribution of the original population, and since it is normally distributed, we don't have to worry about the sample size being greater than 30, okay, because the original population was normally distributed, so samples of any size will yield means that are normally distributed. So in other words, we can use the central limit theorem. Okay, so because we are now dealing with the distribution of sample means, we must use the parameters mean of x bar and standard deviation of x bar, which is our standard error of the mean, And remember, this one is going to be the same as the population mean, but this one is going to be the population standard deviation divided by the square root of n. Okay, so the means are the same, and our sample size is 27. So we're going to have 39, which is the population standard deviation, divided by the square root of 27 is 7.51. The standard deviation comes in, which is going to move the graph in, make it sharper and steeper. And there you have it. Now, when we're talking about probabilities, our standard deviation has moved in quite a bit. Our mean is still here, but now our standard deviation, or our standard error of the mean, is only 7.51. So now is 148 within that. So now we look in here and we say, oh, when we do our z-score, remember we have to use our x, which is 148, and our mean of the x bars, which is the same as the mean of the population. But now we're dividing by a different standard deviation. So our z-score is negative 5.46. That's pretty much way over here. Okay, and it is outside that boundary of the -2 to +2 standard deviations, isn't it? So now it says from table A2, we find that the cumulative area to the left is 0.0001. Okay, so basically we're way to the left, we're almost to 0, but remember the question was finding out what was the probability of having a weight greater than 148, the average of the 27 being greater than 148. And so we're going to take 1 minus the 0.0001, which is 0.99999. We are quite sure that 27 randomly selected adult males will have a mean weight greater than 148. Okay, so again, the big thing is that a single individual, okay, the single individual here, when we go backwards, we had an 85% chance that a single individual would weigh more than the 148. But when we take the mean of all 27, we have a 99.99% chance that we're going to exceed the 148 limit. So there is a 85% probability that an individual male will weigh more than 148, and there is a 0.9999 probability that 27 randomly selected males will have a mean weight of more than 148. So given the safe capacity of the elevator is 4,000 pounds, it is almost certain that it will be overweight if it is filled with 27 randomly selected adult males. Okay, so identifying significant results with probabilities, the rare event rule for inferential statistics. So this is kind of an introduction to what we're going to be doing in Chapter 8, an introduction to hypothesis testing. If under a given assumption, the probability of a particularly observed event is very small, and the observed event occurs significantly less than or significantly greater than what we typically expect with that assumption, we conclude that the assumption is probably not correct. Okay, assume that the population of human body temperatures has a mean of 98.6 degrees Fahrenheit, as is commonly believed. Also assume that the population standard deviation is 0.62, and that's based on some research there. If a sample size of size n is 106 is randomly selected, find the probability of getting a mean of 98.2 degrees Fahrenheit or lower. Okay, so we're assuming that this is our mean of body temperature, and that's an assumption, commonly believed. This one is given to us, 0.62, so we have some data on that, and we're trying to find the probability of getting a mean of 98.2 or lower. So here we go. Now we're dealing with a sample that's 106. Okay, we work under the assumption that the population of the human body temperature is 98.6. We weren't given the distribution of the population, but because the sample size is 106, which exceeds the 30, we use the Central Limit Theorem and conclude that the distribution of sample means is a normal distribution with the mean of the sampling distribution is equal to the original assumed mean, and the standard error of the mean is the population standard deviation divided by the square root of 106, which is 0.62, and small number 0.0602 is the standard error of the mean. So then it says the figure shows the shaded area. See the tiny left tail of the graph corresponding to the probability that we seek. Having already found the parameters that apply to the distribution shown in the figure, we can now find the shaded area by using the same procedures developed previously. All right, so we're saying that the mean we're looking for is 98.2, and when we look at we're going to use our z-score of our standard error. So here, the z-score here, we have the x bar 98.2, but then we're using the mean of the sampling distribution 98.6 and the standard error of the mean 0.06. So we get negative 6.64, way to the left. Okay, so we are going to conclude that the shaded area is 0.0001. It's actually less than that. Okay, so when we're looking at that, we find that z is negative 6.64. It is off the chart, and we're going to use the 0.001, okay, for the cumulative area to the left. So we conclude that the shaded region is 0.001. That's just an easy number to use when we are way off the chart. Okay, so now let's look at this. It says the results show that if the mean of our body temperatures is really 98.6, as we assumed, then there's an extremely small probability of getting a sample mean of 98.2 or lower when 106 subjects are randomly selected. University of Maryland researchers did obtain such a sample mean, and after confirming that the sample is sound, there are two feasible explanations. The population mean really is 98.6, and their sample represents a chance event that is extremely rare, or the population mean is actually lower than the assumed value of 98.6, and so their sample is typical. Okay, so because the probability is so low, it is more reasonable to conclude that the population mean is actually lower than 98.6. In fact, it appears that the true mean of the body temperature is closer to 98.2. And I did not know that before I did this section. You learn something new every day. Okay, so to transform x to a z-score, we're going to use the x bar when we're doing the standard error of the sampling distribution, the standard z-score of the sampling distribution. We're going to use x bar, the mean. These are just formulas that you've already had throughout. Okay, and here's another example. All right, so the graph shows the length of time people spend driving each day. Okay, so here to zoom in on that a little bit. If you're from 15 to 19 years old, you spend 25 minutes, 20 to 24, 52 minutes, and so forth. So this is the average time spent driving each day by age group. Okay, so you randomly select 50 drivers age 15 to 19. What is the probability that the mean time they spend driving each day is between 24.7 and 25.5 minutes? Now, you have 50 drivers, okay, and you're going to, in this age group, and so you're going to compare not individual drivers, but the whole group, and you're taking an average. So you're going to assume that the original population sigma was 1.5 minutes. From the Central Limit Theorem, since the sample size is greater than 30, the sampling distribution of sample means is approximately normal, with the mean equal to the mean of the original population, and the standard deviation, standard error of the mean, is equal to 1.5 divided by square root of 50, or 0.21. Okay, so that's going to end up being our mean time. 24.7 is right there, and the other one, 25.5, that was the region they wanted us to use. All right, so because these are not z-scores right now, we're going to have to turn those into z-scores. Okay, so here they do. They have the original population, and then they're going to show you the z-score, which is calculated with the standard error of the mean and the x-bar instead of individual things. And then they get the z-score that corresponds to 25.5 is 2.36, and they're going to get the probability of the one, the probability of the other. They're going to subtract them and get 0.9116. Remember, when we're talking about the probability in between, we're going to subtract the two of them. So they did not show, they showed the one, but they did not show the other one just because of space. So the other one was negative 1.41 to 2.36. They did that by looking up those, each one on the standard chart, standard normal chart, or else getting them from the calculator. And then they subtracted them, and they got 91% is the probability that is between those two. Okay, and here's a last example. Okay, an education finance corporation claims that the average credit card debts carried by undergraduates are normally distributed with a mean of 3,173 and a standard deviation of 1,120. What is the probability that a single randomly selected undergraduate who is a credit card holder has a credit card balance less than 2,700? So now we're just going to use our regular z-score. Okay, so we're going to take just one person here. So we're going to take mean, standard deviation, probability. This one guy is less than 27,000, okay, and that's going to be a regular z-score, negative 0.42. Okay, we're going to look up negative 0.42 and find the z-score that goes with that. Excuse me, this number, it becomes the negative 4.42, which is our z-score. And then we look at the probability that goes with that z-score. And so we have a 33.7% chance, okay? And then it says you randomly select 25 undergraduates who are credit card holders. What is the probability that their mean credit card balance is less than 2,700, okay? Now, notice that they told us that the original group was normally distributed. The credit card debts are normally distributed. So it doesn't even matter that we're talking about something that is less than 30. Okay, let's go here. So this 25 is not going to be a problem. We can still use our Central Limit Theorem, okay, and because they said that it was already normally distributed. So we're going to have our mean is equal to the original mean, and we're going to get our standard error of the mean in the right calculation, and we're going to find the z-score that goes with it, negative 2.11. That's going to be much less usual, isn't it? It's past the negative 2 mark, and it's going to have a much lower probability, and its probability is 0.0174. Okay, so the conclusion, there was about a 34% chance that an undergraduate will have a balance less than 2,700, but there's only a 2% chance that a mean of a sample of 25 will have a balance of less than 2,700. It's an unusual event. Okay, so it is possible that the sample is unusual, or it is possible that the corporation's claim that the mean is 3,173 is incorrect. All right, so this is just a correction for a finite population, which is in your book, and when sampling without replacement and the sample size is greater than 5% of the finite population size n, then adjust the standard deviation of sample means by multiplying it by its finite population correction factor. There is your homework for 6.3. Okay, not much homework there. And there is your homework for 6.4. Don't forget to do your My Math Lab assignment. And this is Mrs. A, and may God bless your day.